everybody. So in today's lecture, I want to show you some simple code that you can use in calculating potential differences with VPython. Now in general, please remember that when you're dealing with electric potential or voltage, it's always referenced with respect to some 0 point. So, for example, our equation for the potential difference, or for the electric potential phi is equal to kq over r for our point charge. That takes infinity as the reference or the 0 point. And that comes from, of course, if you have the distance here, r, between the source charge q, right, and the point of interest. As that distance increases to infinity, 1 over infinity goes to 0, and so that's our reference or 0 point. Okay? Q in this equation would be the charge in coulombs, and K is the Coulomb constant, which is 8.99 times 10 to the 9th in SI units. Okay? So this is our equation for the potential due to a point charge, and we're going to use that equation a lot today because even if you have a continuous distribution of charges, then how you computationally model that is by breaking it up into little chunks and then treating each chunk as a little point charge. All right, now generally you're more interested in a voltage or potential difference between 2 points than you are in the overall raw value. And that's a little bit kind of like gravitational potential energy, right? Say, for example, our stadium here is at 3,333 feet above sea level. But if you're climbing up the bleachers and you look down, you're a little more worried about the ground right underneath you than you are about how high you are above sea level, right? You're worried about falling. So here we're going to reference with respect to the ground similarly to how you might be more worried about the voltage or potential difference in between 2 points, say points A and point B, than you would be of the voltage with respect to infinity. Okay? So that's what we're going to model here today, the potential difference between 2 points. Okay, now as I said, in previous lectures, we modeled the electric fields due to charges and continuous charge distributions. When we had a continuous charge distribution, we broke it into little chunks or pieces. Now, whether you have a continuous charge distribution or a collection of point charges, what you're going to do is find the field or potential at a single point, and you do that by summing up the contributions from each individual source, point charge, or chunk. Now, in this lecture, I'm going to focus on calculating the electric potential. The electric field lecture you can refer back to another video, okay? But today's lecture, we're going to talk about the electric potential, which might even be a little easier because, of course, it's not a vector. Now, what we're going to do to accomplish that is, first, computationally, you're going to make a list of all source charges and their locations. Second, you would add up the contribution of each source charge to that potential at the sum point A. Then you would repeat that, but find the potential at point B due to those same source charges. Once you've found the potential at A and at B, you then subtract those two in order to find the potential difference between those 2 points. Now, in the slides that I've provided you, I provide also a link to some code that I wrote that you can use as an example, okay? And I'm going to pull that link up now. Okay, let's take a look at it. So in this code, here let me zoom in just a little bit. Okay, in this code, I start off, of course, calling the visual library with our familiar command from visual import star. Then I define my constants. So in the front matter of code, you always want to make sure that you define your constants. So I define the Coulomb constant here. I call it K as 9 times 10 to the 9th. Of course, that's in SI units. Now, what I'm modeling in this code is a dipole. Okay, so this is the potential for a dipole. Now, in a dipole, in this dipole, I've got 2 source charges, and I show them here, and they're called source 1 and source 2. But these source charges each have a magnitude of charge of 2 nanocoulombs. So I define my charge magnitude Q sub E here, 2e to the minus 9. Now, as I said, it's a dipole. Okay, so I have 2 spherical charges. And the positive charge, I've made a red sphere, and the negative charge, I've made a blue sphere. So I've located those that dipole centered about the origin, and I've put my positive charge to the left of the origin by 5 millimeters. So you can see that here. It's a sphere. That's my sphere object. I'm defining my position right here, and the position is minus 0.00500, okay? And so that means it's to the left. X is left, right, okay? Y is up, down, okay? And then it's red, and I give it a radius of 3 millimeters, and I assign the attribute of charge here. Now remember that for any object, you can add on your own attributes. And so when I've done this here, what I've done is I've created an attribute called Q, which stands for our charge here, and then I've given it a value of plus QE. QE I defined previously to be 2 nanocoulombs. Okay, now I do a very similar statement here for my blue sphere, which is my negative charge. It looks very similar. It's just to the right of the origin by 5 millimeters instead of to the left. Now I'm creating a list. Now, honestly, for this code, I probably don't even need to create a list. I could do all of this manually. But I'm trying to set you up for success for future homework problems where maybe you have to do a continuous charge distribution. And of course, for continuous charge distributions, it's much more useful to have all that information in a list. So I'm calling the list sources, and in it I've put source 1 and source 2. Okay? All right, next I'm going to define my points of interest. Okay? So I've defined my point A and my point B. A is a vector located, 2 centimeters to the right and 2 centimeters up from the origin. So it's a vector 0.02, 0.020. And B is similarly defined here as a vector, location 0.12, 0.08, and 0. And you'll see that when we show the code in a second. But it's 12 centimeters to the right and 8 centimeters up. Okay. Next, I'm creating another list. I'm calling it path, and I'm putting my observation points in there. Now, yet again, in this one, I just have 2 points, and, you know, maybe that doesn't seem like a lot. Maybe it doesn't seem worth it. But if you wanted to know what the potential difference was between a lot of different observation points, maybe you'd need a longer list, okay? Now, next, this is a new function or object for us. This is curve, okay? So what does curve do? All right, let me show you the help page for curve. And as you know, or I hope you know, you can look up what the descriptions are of a whole different objects and commands in the VPython help page, okay? So here's the one for curve. What a curve does, it's an object that displays straight lines between points or positions, okay? Now, if your points are close together, you get a smooth curve. If not, you might get a curve that looks something like this, which is kind of a jagged little walking path, okay? So what you do is for your curve argument, you have the different points along the curve in a list like shown. So here, this is the first point, the starting point of the curve, this vector -1, -1, 0, and the second point is this vector 1, -1, 0. And your curve, what it would do is it would create a path that points from -1, -1, 0 to 1, -1, 0. So that's what curve does. And then, of course, as you add more points, you might get, you know, more and more stops along the way. Okay? Now, there's a bunch of different ways to format this, and this help page here shows you some of the different ways that you can format a curve statement. All right? So you'll notice that there's some different ones here. We are utilizing this this way of doing the curve statement, okay, where you're showing the positions of the curve, and then here's the list, okay? So that's what we're doing. All right, so going back to our code, here's our curve statement, okay, and you can see that we've defined path in this way as this list, and then we say that the position of curve is this path. Okay, so that's similarly to what we saw from the help page just a second ago. Now, another thing is you can assign the color for your path. You can make it whatever you want. We decided to make our path green. Okay, now we defined our sources. We've defined our points of interest. So now we're moving on, and we're going to calculate the voltages and potential differences from those source charges at those points of interest. Okay? Now I've got a nice list set up here, and I called it sources. So I thought, why not go ahead and use my for loop to iterate through these calculations. So as you know, if you're going to have a variable within a loop, it's best to go ahead and define that variable before the loop, especially if it's something that you want to update, okay? So here's our loop, for item in sources. So what that means, of course, in a for loop in VPython, you have a list of things, and then here's the list, sources, right? And then what this for loop does is it starts at the beginning of the list and steps through, and then as it steps through, it's going to iterate through the list, going from one to the next to the next to the next. What this for loop does is it calls each one item, okay? So it assigns the variable name item to whatever, wherever we are in sources, okay? I've given a rate statement here. Now, first step, of course, for calculating a voltage or a electric field for that matter, is to define the position vector that points from the charge to the point of interest, okay? So to do that, you've got a displacement vector here, right? I'm calling that displacement vector that points from the charge to point A, I'm calling that R-A, okay? And so then it's final minus initial. So the final would be the point of interest, so that's A, okay, which we defined up here as our vector, right? So that's our final position, and then minus the position of our source charge. Now remember, our source at this point, we're calling it item in the for loop, and I'm referencing the attribute position dot pos from item, okay? So that's my displacement vector. Now I want to update the value of my voltage at point A. So I've initialized it as 0 before I go into my loop, but within my loop I want to update it. So I say, okay, the voltage at point A is equal to whatever the voltage at point A was before, but now we're going to add on this contribution from item, okay? So the equation is KQ over R. So here I have my Coulomb constant K times the charge attribute of item, which is item.Q, divided by the magnitude of my displacement vector, mag of R-A, okay? Then I'm going to do the same thing, but for position B, okay? I define my position vector, and then I calculate my voltage at B, similarly to how I calculated my voltage at A. Now this is going to run through, so every time it goes through, it's going to add on the effect to the voltage at points A and point B for all the different sources. Now this just has 2 in the list, so I could have gotten it all over with without a loop, but like I said, if you've got a bunch of different source charges or a continuous charge distribution, this would be a better way to do it than trying to enter each one of those manually. Alright, once it runs through all of the elements or items in the sources list, okay, then you're going to get kicked out of the loop. Once you're kicked out of the loop, the only thing I ask it to do is to print the values of the voltage at A, the voltage at B, and then the potential difference or voltage difference VB minus VA. So that's what that last statement does. Okay, so let's run our code. And you can see here's our source charges, right? Our negative and our red and blue spheres for our positive and negative charges. This green line is our path, so A and B are there. Okay, so it visualizes the path for us. And then down here at the bottom, the print statement tells us what our values for the voltage are at point A, at point B, right? And then the potential difference, VB minus VA. Notice that we're a little closer, since we're on the right-hand side here, and so is the negative charge, we're a little closer to our negative charge, and so that's going to dominate in our potential terms. That's why we have negative values for the potential at A and B, because we're closer to B, to the negative blue charge, than we are to the red. Okay? And then our voltage difference is 150 volts. So as we walk from A to B, we actually increase our voltage by 150 volts. All right, I hope that was straightforward and that you understood that. That code is available to you at any time. I hope it helps you with your homework, and I'll see you later.